And so we're very glad to have Leonardo Larizza today from the University of Coimbra, who will be talking about lax factorization systems and categories of partial maps. So you can start when you're ready, Leonardo.
Thank you, and thank you for your invitation and your introduction. Today I'm going to talk about some results developed during my PhD, my current PhD period in Coimbra under the supervision of Professor Maria Manuel Clementino. And I will be talking about a new kind of factorization systems of our introduction and discuss them along with some instances that we developed in the context of categories of partial maps. So I'll briefly explain what I'm going to talk about. First, I will recall some notions about partial maps and their order enrichments. Then I will explain, I will define a new notion of orthogonality, in particular lax-weak orthogonality, which will be the base concept on which this theory is built. Then I will proceed to describe these lax factorization systems of our introduction along with their properties. And then I will focus on some lax factorization systems generated by total maps among partial maps. And moreover, I will discuss a link between OP-lax weak factorization systems for a category of partial maps and some weak factorization systems that already are on the base category. I will then present how these constructions apply to the category of sets with partial maps. And I will conclude presenting some open problems that weren't solved yet and that are still something that we wonder about for some pointed order enriched categories. So first of all, I recall that as usual, by an order enriched category C, I mean that on this category, there is defined a partial order among morphisms in the same home set. And this partial order relation must be compatible with compositions. So whenever I have a two cell from F to G, this must be preserved by composition with the same morphism on the left and on the right. And whenever I consider an order enriched category C, this gives rise to a category that we will denote C2 lax, whose objects are morphisms of C, and whose morphisms will be lax commutative squares as they are depicted in the diagram. So whenever I say that I have a lax commutative square UV from F to G, I mean that this square is no longer commutative, but only involves a two cell directed, and as in the diagram. Then, considering a category C with pullbacks and a class of monomorphisms S, which is closed under pullbacks and composition, usually it is defined that a partial map is defined as a span, as in the diagram, a span of two morphisms, the first one being in the class S, while the other one is a general morphism in the category C. I will use this notation sigma, phi, and d to denote the left part, the domain part, and the domain component and the function component of a partial map. And in particular, I will say that whenever the domain component is actually an identity or an isomorphism, then we call the partial map total. We say that the partial map F is total. These morphisms, these partial maps with the object of the category C form a category, the category of partial maps built on C, along with a composition law that is defined via pullback. So whenever we can write in sequence F and G, the composition will be built via pullback. And by the property of S, we know that this is again a partial map. Moreover, for any category of partial maps, we can build a partial order among arrows, therefore an order enrichment that is defined as follows. We say that we have a two cell from F to G whenever there exists an arrow in S, such that these two parts of the diagram are commutative. So we want to have that S gives commutativity on both on the left leg and on the right leg of the span. We will call this order enrichment discrete order enrichment, and it carries the following properties. First of all, whenever F is total, then it is maximal with respect of this order enrichment. So whenever we have a two cell from F to G and F is total, then F is equal to G. And moreover, whenever we have a composition of G composed F and the composition is total, then F is total as well. We may also give a different notion of order enrichment. If we consider a category C, which is order enriched as well with this square order relation property, order relation, and morphisms in S are faithful, then we give the following definition of order enrichment. We have a two cell going from F to G whenever there exists, again, an arrow S in the class S, such that the domain component is still commutative in the diagram here, while on the function component, we only require a directed two cell in C. This time, total maps will not be maximal in the sense as described before, but whenever we have a two cell going from F total to G, then G is total as well. And we have the same property about compositions that are total among partial maps here.
Can I ask one question, actually?
Sure.
When you define this category of partial maps, do you not need to take equivalence classes of spans?
Yes, we do.
Okay.
Yes, and by equivalence class of spans, I mean that the domains are equivalence classes of monomorphisms, so they are subobjects.
Okay, so these are equivalence classes of spans?
Yes.
Okay, thanks.
And this construction in particular can be carried out for sets. Set is a suitable category for this construction. We have pullbacks, and we consider equivalence classes of monomorphisms here among morphisms, among functions in sets. And we remark that domains of composition are just what we would expect are pre-images of the second domain of a composition of two functions. And in particular, the discrete order enrichment that I have defined before actually turns out to be the relation of being a restriction of having a two cell from F to G is equivalent to say that F is a restriction of G. Then we come to the first concept, the first notion of our introduction. We say, which is Lax-weak orthogonality. We say that in C, an order-rich category, two morphisms are Laxly weakly orthogonal, which is denoted by this symbol here. If for every Lax square from F to G, we have a morphism D forming these two triangles in the picture, in the diagram, and entailing the two cell in the diagram. In particular, we will call this morphism D Lax diagonal morphism for the Lax square UV. As it happens for usually for the traditional case of weak orthogonality, we can define orthogonality also between two classes of morphisms. We can define Lax weak orthogonality between two classes of morphisms. And it just means that for every pair of morphisms, one in each respective class, they all are laxly weakly orthogonal one with respect to the other. And we can also build complement as usual, build left lax weak orthogonal complement, and which is the second one, and the first one, the right lax weak orthogonal complement. I'll quickly recall that, as usual, in an order-enriched category, we say that we have an adjunction F left adjoint to G, which are both morphisms in C. Whenever we have a unit 2-cell and a co-unit 2-cell, as in the equation here. And we have that for any morphism in C, F is laxly weakly orthogonal to itself if and only if it is a left adjoint, and this is equivalent to have that F is laxly weakly orthogonal to any other morphism of C to the left and to the right. In particular, whenever we have a morphism which is laxly weakly orthogonal to itself, if we consider the identity square, we obtain we have a lax diagonal morphism for this square, and this lax diagonal morphism actually turns out to be the right adjoint to F, and this is clear by the two cells formed in the diagram. Moreover, whenever F is a left adjoint, then we can build for any lax square UV going from F to any G in C2 lax, we can build a lax diagonal morphism by composing U and F star. And this in particular also implies that F is orthogonal to itself. And with these two arguments, the rest of the proof is trivial when it is not only analogous to that. In particular, if we consider partial morphisms, partial maps, we consider C an order-enriched category, so we would like to build the general notion of order, and PC a category of partial maps. Then we have that two partial maps form an adjunction F left adjoint to G, whenever F is total and its function component is equal to sigma G composed phi bar F. I will explain in some seconds what this phi bar F is. And moreover, if the phi bar F is a left adjoint in C to phi G. So we have an adjunction in C, and G is the function component of G is a right adjoint in C, and the left component, the function component of F is a left adjoint composed with an element of S. In particular, we remark that whenever the order enrichment that we are considering is discrete, is the discrete one that I have defined before, then a pair of morphisms constitute an adjunction if and only if they are of the following form. So F must be total again and just a sigma element of S, and its right adjoint will be sigma and an identity. And this is because if the order is discrete on C, then adjoint pair are just reversed inverse morphisms. I'll give a quick sketch proof to explain the proposition before. First of all, we consider an adjunction F left adjoint to G in PC, and considering the unit 2-cell, we notice that G composed F must be total, and therefore F must be total. Then we proceed to write explicitly the two cells entailing the unit and the two cells for the unit and the co-unit among partial morphisms. And in the first part, we notice, first of all, that by totality here, we have that the pullback of sigma G along a phi of F is an identity, and therefore here comes out the phi bar F that I mentioned in the proposition. and always from the unit we obtain the unit to cell in C that we need to prove. And moreover, if we look at the co-unit here, we have this to cell, which is written here as an equation, which is actually the co-unit to cell that we are seeking in C, in this guise because it is composed on both sides here and here with sigma g that is faithful, and therefore we can cancel it and obtain the co-unit to cell. And this concludes the fact that this concludes one direction of the proposition of the statement, and the other is proved directly, since piecing together all of the properties, we are able to rewrite these two diagrams that define the adjunctions, the adjunction in PC. Now we come to the definition of the first type of a factorization system. This one being the Lax-Wick factorization system. First of all, we say that a Lax-Wick pre-factorization system is a pair L and R of classes of morphisms, such that R is the right Lax-Wick orthogonal complement of L, and L is the left Lax-Wick orthogonal complement of R. Moreover, if any morphism F admits an LR factorization, we call LR, the pair LR, a Lax-Wick factorization system. I'll quickly remark that for any Lax-Wick pre-factorization system, the intersection between the two classes of morphisms it is actually given by left adjoint morphisms of C, and this is clear by the last proposition that I have stated. Moreover, we have analogously to what happens for the traditional case that we can complement a class of morphisms in C2 Lax two times, so obtaining the complement and the double complement, and this gives rise as well to two Lax-Wick pre-factorization systems. We come now to describe another kind of factorization system. First of all, I recall that by this notation, I mean I define the composition factor going from pairs of composable morphisms in C2 Lax to their composition. And then I proceed to define a Lax factorial factorization system as a factor F going from C2 Lax to the category of pairs of composable morphisms, and such that whenever it is composed with the composition factor, it gives back the identity. So whenever I apply the composition factor to F of any factor, it gives back of any morphism, it gives back the first morphism. In particular, again, I can compose the F with the projection of the product of C2 Lax, and then I obtain the left component factor, the right component factor, and the factor that yields the middle term of the factorization. And to avoid ambiguity, I will denote a Lax factorial factorization system always with all of its components. And as well as in the traditional case, here we also have two natural transformation, eta and epsilon, going from the eta from the identity to the factor R, and epsilon going from the factor L to the identity. And these natural transformation are defined as usual, going from F to RF through the composition and vice versa. But we remark that differently from what happens for the traditional case, these transformations are not strict in general, but only of Lax. Meaning that if we consider these two diagrams, the first one being UV composed with eta G, and the second one being eta F composed with R of UV, this last square, Lax square. Then we have that by definition of F and of L, LGU, we have a two cell going from LG composed U to KUV composed LF. So we have a two cell going from the top edge of this rectangle to the top edge of this rectangle. And this amounts to have not a commutativity between these two elements, eta G, UV, and RUV, eta F, but only a one direction two cell. And therefore, this transformation is Laplace, as well as similarly, one can notice that epsilon is an Laplace natural transformation. Now we would like to merge the two definitions. So first of all, I say that a Lax-weak factorization system LR is functorial whenever there exists a Lax functorial factorization system FLRK, such that the factorial factorization are also LR factorization in the Lax-weak factorization system. And then I would like to consider whether any Lax factorization system yields Lax-weak. Every Lax factorial factorization system yields a Lax-weak factorization system. So I consider any FLRK to be a Lax factorial factorization system, and I define the following two classes: LF given by those morphisms that are left Laxly weakly orthogonal to their right component, and RF dually those morphisms that are right Laxly weakly orthogonal to their left component. And I say that this Lax factorial factorization system is pre-distributive if for every morphism F, LF lies in the left class and RF lies in the right class RF, which amounts in particular to have the following two orthogonality relations for any F. Then I'll just point out that the definition of these two classes was given for any Lax factorial factorization system, not just for Lax predistributive, but whenever the Lax factorial factorization system is Lax predistributive, then I can give the following equivalent definition to those classes, considering LF the class of those morphics that has a Lax diagonal morphism for the square eta F, and respectively RF, those that have a Lax diagonal morphism for epsilon F. And this is different because now we are only entailing the existence of a Lax diagonal morphism for two particular squares and not for any squares that goes from F to RF or from LF to F. And we will denote this particular lifting for the unit and co-unit transformation by rho F for the one that appears for an element of LF, and lambda F for an element that belongs to RF. Then just a consideration on why this definition is equivalent. On one sense, of course, it is trivial since eta F and the epsilon F are actually Lax square entailed by the orthogonality relation. But on the other hand, whenever we consider F such that rho F is a Lax diagonal morphism for eta F, then we consider any other Lax square UV from F to RF. We build the factorization of this Lax square along F and RF. And now we have rho F by hypothesis. Lambda RF exists due to Lax predistributivity, and this yields the existence of a Lax diagonal morphism delta given by the composition of these three morphisms: lambda RF, KUV, rho F. And therefore, F is Laxly weakly orthogonal to its right component.
May I ask a question here?
Yes, sure.
In the definition you gave, the word weak vanished from you have a Lax-weak factorization system, a weak orthogonal system, and then you had just the weak didn't exist anymore in the factorial case, right? It's just a matter of definition, right?
in the slides, in which definition?
On the last definition you gave, you said yes, a weak factorization system is functorial if
we say yes. The difference is that we have a lax weak factorization system, and it can be also moreover functorial. So we have a lax weak factorization system, a lax functorial, and the intersection of the two is a lax functorial weak, or a lax weak that is also functorial.
Yeah, my question is why, is there a good reason that you don't call it a functorial weak factorization system? Why is there no weak in there, but there's a weak in the first one? Does that question make sense to you?
Yes.
So in the non-lex case, weak means basically is a condition on the uniqueness or on the special on that lift being special in some sense, right?
Of not being special. Yes.
Not being special, exactly. Yeah.
Yes.
And when you leave that out, it usually means there is a special arrow.
Yes, but also we have, just considering the traditional case, we just have factorial factorization system that are not weak, but we have a factorial factorization system that has an underlying weak factorization system. This is what I want to point out. Whenever I have weak, it means that there exists an underlying weak factorization system.
Yes, but the functorial factorization system is, so, I mean, I would imagine that that in the lex case, not being weak, being a lex factorization system would mean something that the diagonal lift is something initial or somehow minimal, that there's a minimal such lift. So so I would expect, reading that definition, that maybe functorial factorization system means there's a functorial choice of such minimal lifts rather. So there. Otherwise, I would expect it to be called functorial weak factorization system. Is that?
Okay, well, the fact is that by lax factorial weak factorization system, we meant another notion, which is just a factorial factorization with an underlying weak factorization system. Probably there is a better way to express that, but that's why there is no weak here.
Okay.
Can I ask a question? I'm a bit lost as well. Is the functorial factorization system, in this sense, literally, a functor from the category of arrows to the category of composable pairs, which is a section for the composition functor?
Yes.
Is that what
yes, it is.
Right. Yeah. So it's just that. So there's nothing weak there, right?
No.
Or there's nothing lax there.
Well, it is lax because we are also considering.
You have those lax squares.
So it also means that here, for example, we don't have. We would like to factorize also lax squares and have lax squares here, which simply factorial factorization do not cover. It does not cover this case. So the fact that this factorial factorization goes from C2 lax to the product of the C2 lax times C2 lax amounts to have factorization also for D squares in this sense. This is the difference between the traditional not enriched case.
Okay. Thanks.
Okay. Thank you. I think I was here. Yes. So due to the properties and the proposition that not the proposition, sorry, the properties that I have just discussed, we have that for a predistributive lax factorial factorization system given by FLRK, if it is predistributive, then LFRF is a lax weak factorization system. And moreover, for any lax factorial factorization system, R that underlies a factorial factorization given by those elements, then it is built through the definition that we are given from LF and RF. it is exactly given by those morphisms with those lax-weak orthogonality relations. I'll briefly show that whenever I take an F in LF and G in RF, built this way from a lax factorial factorization system FLRK, then we consider any lax square UV going from F to G, and our objective is to prove that they are orthogonal. And to do that, we use simply the two morphisms rho F and lambda G that we have by predistributivity, and we have also due to the equivalent definition of LF and RF. So we have a lax diagonal morphism in this lax square given by this delta. And moreover, we have that whenever F belongs to RF, it is left laxly weakly orthogonal to RF. It is in particular laxly weakly orthogonal to its right component, and therefore lies in L. And by analogously, we have the other inclusion, which concludes the fact that LF and RF form a lax-weak factorization system. Before proceeding to give the last definition of lack of factorization system, I recall that in an order-rich category, by lax monad, we mean a triple given by T, eta, mu, where T is a locally monotone functor from C to C, a locally monotone endofunctor. Eta is a Knoplux transformation, and mu is a Knoplux natural transformation as well, the first one going from the identity to T, and the second one going from TT to T. And they must satisfy the following lax monad axioms, as in the picture, and as it is usually defined. Then we say that a lax algebraic quick factorization system is given by a functorial factorization system, such that R eta is part of a lax monad and L epsilon is part of a lax comonad, which is the dual definition of the lax monad, obviously. And moreover, if there exists a distributive law delta of the comonad over the monad that satisfies the following diagram, such that the following diagram commutes. And we have in particular that any lax algebraic quick factorization system is predistributive, and therefore it has an underlying lax weak factorization system, which is described as before. And we focused on the lax case, but I should mention that dual arguments can be carried out for C2 Oplax, and therefore we have an Oplax weak orthogonality relation denoted in this way that requires again the existence of Oplax diagonal morphisms. And I shall mention that the difference here is sensibly the fact that self-orthogonal morphisms are now right adjoint morphisms, and that for Oplax functorial factorization systems, the transformations that we obtain are lax natural transformation, eta and epsilon. So now I'll come to focus again, to study again partial maps. We consider C order-enriched and a category of partial maps built on C. Here we are considering the general notion, the general definition of order enrichment given by the order enrichment that C has. And we consider, we see that for any morphism, for any partial map in PC, we can factorize it in the following way, considering in the left component just the domain component, and in the right component just the function component through a total map. And we say we prove in particular that this factorization is factorial. Well, actually, it is a known fact that this factorization exists, and it is factorial, and moreover, it is lax predistributive. it is Lax distributive, and therefore one can ask what are the two classes, what is the definition for these two classes, and for the left part we have that morphisms that belongs to LF are partial left adjoint, meaning that they are their function component is given by a sigma in S and a phi bar F, which is a left adjoint in C. The difference here between a partial left adjoint and a left adjoint is that a partial left adjoint is not total, and it is not therefore a left adjoint. And the right part is given by total maps. The intersection does make it is consistent with what we have said before, because it becomes total partial left adjoints, which are actually left adjoints. And moreover, this Lax factorization system is also Lax algebraic weak. Functoriality and the construction, the definition of Lax monads and comonads are carried out naturally, so it is a natural check to do. Moreover, we focus on the equality between partial left adjoints and LF. We consider an F in among partial left adjoints. Then we notice that the RF is a left adjoint morphism by definition of RF, and therefore it is left Laxey weak orthogonal to F, and then we have that F belongs to LF. And on the other hand, whenever F belongs to LF, one can consider the Lax diagonal morphism for eta F, and through this morphism, one builds the needed sigma delta and phi delta to prove that phi F is a partial left that F is a partial left adjoint. And then whenever F is total, then LF is by definition an identity, and therefore we have that F belongs to RF. And on the other hand, whenever F belongs to RF, considering delta prime a Lax diagonal morphism for epsilon F, actually this one is lambda F. And we just consider the identity to cell, and by properties of the order enrichment, we have that LF is total, and therefore by definition it is the identity. And this concludes the fact that RF is given by total morphisms. And in conclusion, we actually see from the definition that LF is a partial left adjoint, since its function component is always an identity, and RF is a total map, obviously by definition. We come now to consider a link between Oplak's weak factorization system on partial maps and weak factorization systems on the base category on which partial maps are built. So we start with the category C with a stable weak factorization system EM on C. By stable, I mean that the left class of morphisms E is stable under pullback. So the same definition that one has for stable orthogonal factorization systems. And we proceed to factorize any partial morphism F. First of all, considering the factorization of its function part, and then giving the following part of factorization composed by the domain part and the left part of the factorization of phi, and the total right part of the factorization of phi F as well. We have here the for a factorization of F. We would like to know which kind of factorization it is. First of all, we define E bar and M bar given by those morphisms whose function component belongs respectively to E and M. One proves that these two classes are actually Oplak's Oplaxly or weakly orthogonal one with respect to the other. And to prove this, one actually needs stability under pullback of E. So here it is where this property is used. And moreover, whenever EM is functorial in the traditional sense, then one can extend the functorial factorization on C to a functorial to a no-Plax functorial factorization on PC. And the definition of the two components is given here, and these are proven to be functors for PC2-Lux. And in synthesis, we have that the pair E bar and M bar is a no-Plax weak factorization whenever EM is a stable weak factorization on C. Moreover, if it is functorial through FLRK, we can extend the functorial factorization to a no-Plax functorial factorization on partial maps. And furthermore, if it is algebraic weak on C, if it is an algebraic weak factorization system, the extension is a no-Plax weak algebraic factorization system on partial maps. Then we come to apply the discussed properties and construction for P-set. P-set being the category of sets equipped with partial maps. Here we have that left adjoint partial morphisms are given by injective total maps, and the right adjoint morphisms are given by partial bijective maps. So first of all, we have that here as well. I should mention that the class S is given, as I said before, by equivalence classes of monomorphisms of monos. And okay, I was saying that we have, as we said before, a Lux functorial weak factorization system, actually a Lux algebraic weak factorization system given by monobar and total maps. Monobar here is actually given by, it is equivalent to have a partial left adjoint, since since left adjoints are total, given by a total and a monomorphisms on the function leg. And so we have this Lux algebraic weak factorization system. Moreover, we know that mono epi is a weak factorization system in set, and of course, mono is a stable class of morphisms under pullback. Then we can build monobar and epibar, and it is a no-Plax weak factorization system in P set, in the category of partial maps among sets. And in particular, we build from any factorization of F among sets of any factorization of Pf, sorry. We can build two factorizations. We can be one for each factorization. The first one given through products, and the first one given through coproducts. These are usually factorization mentioned to prove that mono-epi factorizations in sets are not unique. And we also have that epi mono is a stable orthogonal factorization, therefore is also algebraic weak. And then we have that it is stable because epimorphisms among sets are stable under pullbacks, since it is are stable under pullback. And we can build epibar, monobar, which is a no-Plax algebraic weak factorization system. And again, we can extract from any factorization, epi-mono factorization of F, an epi-mono factorization, epibar, monobar factorization of a partial map F, as in the diagram. I shall now come to the last part of this talk, which is about some open problems for pointed categories. The objective here, the aim here was to generalize some behavior that that we have on sets with partial maps. So before going to the open problems, I shall describe what happens for P sets. In particular, we start considering the empty set here, and we remark that it is a zero object in sets of partial maps, and zero morphisms are given by spans of the initial morphisms in set, simply. And we consider the class O given by all zero maps in P sets for any pair of objects in set. And we would like to apply to the class O the property of complementing and double complementing O to obtain a Lax-Weak prefactorization system or a not Lax-Weak prefactorization system. In P-set, actually, this process gives rise to total for the left Lax complement of O, and to left adjoint to the the right total are the right Lax complement of O, and left adjoint are the left Lax complement of O. And the first one, we know it is involved, it is entailed in the Lax factorization system monobar tot, and Lax-Weak factorization system, sorry. And the second one is given by the trivial Lax-Weak factorization system left adjoints all other morphism. If we complement through the, if we complement with respect to the Lax-Weak orthogonal property, we obtain on both sides of O epi bar, which is in set part of the two Lax-Weak factorization systems that we have described before. And the question is whether this behavior that here is successful and in 3 times out of 4 it is also not trivial, whether this behavior can be generalized. So we consider a northern-rich category C that has an initial object I, and such that all initial morphisms are minimal with respect to the order enrichment of C. Then we remark that I is still an initial object for PC, for the category of partial maps built on C. And moreover, if I is either a zero object or a strict initial object, we have that I is a zero object for PC, for the category of partial maps. Then we consider the class O of all zero morphisms or the pair of initial morphisms if I is not zero here. We consider O, and we have in particular that for PC a minimal map F such that the partial domain is I, so a minimal a map in O is always right absorbent. And by right absorbent, I mean that composition on composition to the right with any other morphism still gives a morphism in O. And whenever I is a zero object, it is of course both left and right absorbent. Composing zero morphisms on the left or on the right gives back a zero morphism. Then we would like to look at complements. The first, the left Lax-Weak orthogonal complement of O can be described as follows. We consider F in this class. Then F, that we always have the Lax square going from F to the zero map through the identities. And the bottom triangle, the true cell in the bottom triangle always exists due to the properties of O, while the top triangle, the top triangle involves a true cell if and only it actually is an equivalent condition to have that F belongs to this complement. So here, this completely describes the elements in the complement of O, in the left complement of O that we will call U. In particular, I shall remark that in the partial, whenever the partial order is discrete, then if we look at this true cell, this yields that F is a split mono by equality of because this one turns to be an equality, and for partial maps, and therefore it is a left adjoint morphism, and this is consistent with what happens for sets. And we conjecture that actually, considering what should happen for the intersection of the two classes of a prefactorization system, we conjecture that the right orthogonal complement of U, Lax-weak orthogonal complement of U, is given by those morphisms that have a co-unit to cell. But still, this wasn't. We weren't able to prove this conjecture, so it remains an open problem. Considering the other Lax-weak orthogonal complement of O, we then have that if F belongs to this complement, whenever we have a Lax square here from a zero map to F, there must be a Lax diagonal morphism. First of all, I recall that to have a Lax complement, a Lax square here from 0 to F, this implies that by minimality of zero maps, this implies that F composed U is a zero map as well. And then whenever we have this two cell delta composed zero from U to delta composed a zero map, this implies that U is zero. And this turns out to be a necessary and sufficient condition for the existence of such delta. And then we define, then we can give the definition of the complement of O, DD, which stands for dense domains, which takes inspiration from the case of partial maps. And these are described as follows. Whenever F composed U is equal to a zero map, then U must be a zero map. Those are the F that belong to this complement. But it is still an open problem to verify what is the double complement, the complement of this class. And I only remark that in set, this is the case where we have total maps. Therefore, this class of dense domain maps turns out to be total maps. But in general, this is not true. And we have counterexamples for abelian in the category of abelian groups. And this is a span which is in dense domains morphisms, but it is not total, of course. We have other counterexamples also in topological spaces, open topological spaces. So this is only an inclusion, which in general is not an equality. And similar arguments can be carried out for the Oplaks case as well. Here we have the dual property regarding to have a dense image, or namely F such that V composed F is a zero map implies that V is a zero map. And again, we weren't able to describe the complement in general, as well as the Oplaks right weak orthogonal complement of O is given by those maps that have again a co-unit, but now they are candidates to be a right adjoint, a unit, sorry. And we conjecture as well that the complement is given by those morphisms that have a co-unit to cell, and they are candidate to be right adjoint as well here. Again, considering what the intersection between the two classes should be. And these problems are still open. It has proven to be difficult to give a general description, but it would be interesting to find new examples to have more properties and consider a more general behavior than the one that we had in set. And so any suggestion is welcome. And with this, that was all I plan to say in this talk. I'm giving here an essential bibliography. The first one is the paper that I have written and it can be found on arXiv, where all of these topics are covered. And the other three papers were very helpful, and they were also an inspiration to the current work. And thank you for your attention.
Okay, thanks very much to Leonardo. So we have our usual silent round of applause. So thanks for a nice talk. And if anyone has any questions, feel free to go ahead and ask.
Can I have a question? Could you go back on slide number 31?
31, yes. 21.
Yeah,
Yes.
so here's this proposition, and the question is that, is there some kind of um, uh, small object argument which would say that if in this class H the domains are small in some sense, then this Lux-weak prefactorization system is a weak factorization system as well?
Okay. I'm not sure about it. It makes sense. There should be, but I don't have a proof for that. But it could be an interesting property to an interesting result to add, actually. But I can say yes for sure at the moment because I didn't prove this fact.
Thank you.
Thanks.
Yeah. So first of all, I would like to apologize for the last question. It was rather stupid. I realized afterwards that I didn't really understand what the definition was saying. Second, I guess a natural question is, so in the beginning you were talking about order-enriched categories in general and their weak factorization system on it. So a natural question would be how much of that works out if you replace ORT by cut. So, or, you know, you have some notions of two categories.
Most of it, I should say that the most theoretic part actually can be carried out for two categories. It is not present in the work, but during the preparation of this work, we prefer to focus on order-enriched category to be clearer in the calculation. But actually, this can be carried out for two categories as well, with sensible remarks about whiskering through cells and so on. But most of it can be carried out also for two categories in general.
Okay, cool. Thanks.
Can I ask a question? If you go back to the original the early definition, I think of lax-weak orthogonality.
Yes.
Yeah. So you could also consider the order relation between lax squares, and so for example, if you had on the top u is less than u prime and
yes.
v is less than v prime, does that give you some d is less than d prime? So essentially you're considering, it seems that you're considering the sort of RO category just as a category and not as an order-enriched category. And I'm just wondering if there's a reason for that, or if you have considered, I mean, one could strengthen this definition, right? Yes. By asking for an extra condition about sort of two cells in this order-enriched RO category. Does that make sense?
Yes. Well, yes. I didn't prove anything about that. The definition doesn't require this property, but I have considered this property since the inspiration comes from lax orthogonal factorization systems, which are introduced by Professor Clementino, and that actually have a minimal property about diagonal liftings. So this property was considered in the construction of this definition, but at this was a first step to then attempt to approach that property in a further development of this notion. So at the moment in this study, minimality of D with respect to this kind of ordering among lax square wasn't taken into account. And the objective was to reach that property maybe with a more complex definition of factorization systems or of orthogonality as well. But in this definition, it is not entailed. It could be, it is actually, it is interesting to wonder what this would imply and add to the to this theory.
Okay, so it's still to do, future work maybe, or is that right? Or
yes.
And one other question is just, so you have this construction that takes a category C equipped with a weak factorization system,
yes,
to I think word enriched category equipped with some kind of lax weak factorization system. And I was just wondering, does that have a universal property of any kind?
Can I ask you to repeat the question? Sorry.
Yeah, well, there's the sort of thing which there's the map maybe functor which sends C to PC.
Okay.
And moreover, so if so if you have CEM, so a stable weak factorization system, then you get PC, maybe PE, PM, I don't know what to call those classes, but so that takes you from the world of weak factorization systems to the world of OPLAX weak factorization systems. And I'm just wondering whether that assignment has a universal property. Is it the universal OPLAX weak factorization system, or that you can construct from a weak factorization system? Maybe it's...
well, okay. To answer to that question, actually, something that is present in the paper, but not I didn't mention during the presentation, is that one can also restrict a no-plux weak factorization system on PC to a weak factorization system to C, and this happens only for OPLAX weak factorization systems, not for LAX. So yes, there is a universality in the sense that from a stable we get a general OPLAX weak factorization system, and from an OPLAX factorization system we get a weak factorization system.
Okay, and so are they adjoint functors in any sense, or? I guess that's my question.
I guess so, but I can't say it. I can say that I have an explicit proof for that. Maybe it is worth to check before.
Okay. Yeah, it might. Well,
but I imagine that it should work fine. Yes.
Okay. It might be something interesting to look at because it might explain a universal property of the category of partial maps or something like this. So
yes, that's actually interesting. Yes, thank you.
And maybe last question from me, are there any examples related to the word-enriched categories of topological spaces and things like this? So I know people consider word-enriched categories like that.
At the moment, not that that I have found. It has been proven to be more difficult to build LAX or OPLAX factorization, weak factorization systems in that context at the moment. So I don't have other examples outside of the case of partial maps. Okay. Except for those pointed categories, but still it is not a concrete example. It's just a way to build it in a pointed category that has nice properties, actually. Okay, thanks. Does anyone else have any questions?
Maybe a vague one. So you defined this notion of Lex weak factorization system in that general setting, and then you looked at many examples in partial maps over something, right?
Yes.
Is it fruitful to look the other way around? So I suppose you could. This is not very well thought out, but it looks like you could look at the through the lens of partial maps at Lex weak factorization systems, in the sense that if you go to the definition of what that is you take a 2-cell and you factor a 2-cell into 2 other 2 cells. Yes. So in some sense, it is a partial functorial factorization on 2 cells.
Yes.
Does that make right? It kind of looks like it. So I wonder if it's maybe if it makes sense to look at this general setting, in fact, in terms of your examples.
Well, it is worth to want to think about it maybe in this sense, in particular, since partial math has been proven to be more fruitful than other contexts to provide this kind of examples. At the moment, since as I said, I wasn't able to provide any example outside the context of partial maps. I also wasn't able to have a comparison terms by which I could, for instance, consider how much another category that has a no-Lax or a Lax weak factorization systems resembles a category of partial maps. And so that could be one step to try to think whether to distinguish this notion from the partial maps context or not. Mm-hmm. So that could be one step to approach this question. I see the point of that. Yes.
Okay. Well, if anyone has a last question, go ahead, maybe. Or if not, then let's thank Leonardo again. Nice talk.
Thanks to you. Thank you for the invitation.
And so next week we have Giulio Lomonico talking, and so that will be our last talk of the semester. So we can